Hello and welcome to my talk titled A Computational Approach for Objectively Derived Systematic Review Search Strategies. My name is Harry Scells, and this research was undertaken during my PhD in collaboration with ECIR and the Bond Institute for Evidence-Based Healthcare. What are systematic reviews? A systematic review is similar to a literature review. They are the synthesis and appraisal of all relevant documents for a particular research question. Their aim is to be unbiased and comprehensive, and it must adhere to strict guidelines and protocol. This ensures the review can be reproduced. There are many uses for systematic reviews, but in the medical domain, which is the area of this talk, systematic reviews guide clinical decisions, for example, what actions a clinician should take to treat and diagnose patients. They inform institutional practice and policy making. There's a famous example of a systematic review being used to assist banning of smoking tobacco in public areas in the UK, and they provide evidence through comprehensive literature review. They form the cornerstone of evidence-based medicine. Here is a high-level overview of the systematic review creation pipeline. There's many steps in this process, and throughout this process, studies are gradually refined. A research question comes in the top, and at the bottom a systematic review is produced. But there's a big problem here, which is that these steps are time-consuming and costly. A systematic review can cost upwards of $150,000 and take more than 2 years to complete. To address this problem, my research focuses on improving how queries are formulated. However, there's also quite a lot of research which is focused on automating the appraisal of literature, which is the screening phase. Queries for systematic review literature search are highly complex and therefore difficult to construct. Specialist librarians called information specialists formulate these queries. They target literature databases, for example PubMed, which is one of the largest and most prominent and commonly used literature databases. PubMed alone has approximately 30 million studies indexed at the time of this talk. All of these literature databases use Boolean queries and Boolean retrieval as a consequence to allow information specialists total control over the search system. Often the development of a query is seeded by a set of known to be relevant studies, a protocol for the systematic review, and a research question. A recently proposed methodology for developing queries for systematic review literature search is called the objective method. This method aims to be less subjective than existing query formulation methods by exploiting term statistics. The method of formulation for the objective method is as follows. First, a test set of seed studies is identified and then divided into a development and validation set. Next, terms from the development set are ranked by document frequency and the top 20% are kept, so there's a filtering step on the terms. Then, another set of terms are filtered again from a population or background set. The bottom 2% of terms are ranked by document frequency, then are filtered. The population set is derived from an empty search to PubMed, which retrieves the 10,000 most recent studies. Next, a set of mesh terms are identified from studies in the development set. Mesh is an ontology of medical terminology used to classify studies in PubMed. Mesh terms can be added to PubMed queries to filter studies to those which include the mesh term. Then terms are added to one of 3 clauses in a Boolean query which relate to health conditions, the treatment, or type of study design. Finally, the constructed Boolean query is evaluated on the validation set to determine the effectiveness of the query. However, there's some limitations to this approach, which is that there's some manual and therefore subjective or biased processes in this otherwise objective methodology. For example, these parameters which are used to filter out terms could be tuned automatically. The way in which terms are added to the query is also subjective, and we could automatically categorize terms and filter them to those which are contributing the most to retrieval. Finally, we recognize that in order to tune parameters using the validation set, we would need to use another set of studies for evaluation. Therefore, we use the validation set to tune parameters and evaluate on a new unseen set. We address each of these problems by computationally adapting the existing objective method. First, instead of splitting the test set into development and validation, we split it into development, validation, and unseen. Next, we use the validation set to tune the optimal document frequency parameters when analyzing the development and population sets. Then, to add terms to the query, we can automatically map these terms into UMLS concepts to classify them using their semantic type. We do this using MetaMap. UMLS is an umbrella ontology, which includes many other medical ontologies, for example MESH, SNOMED, among others. Then we can automatically determine the minimum number of terms that retrieve the validation set and optimize the query towards an evaluation measure, in order to maximize that evaluation measure on the validation set. And then finally, we can evaluate more fairly on an unseen set of documents. For our experiments, we instantiate this computational objective formulation pipeline in a number of ways. The first is that we make the addition of mesh terms optional to study the effect mesh terms have on query effectiveness. And the second is that we optimize queries using the validation set using a number of evaluation measures, for example, F measures and recall. Now, with an understanding of the objective methodology and how we computationally adapt the objective methodology, we can have a look at some of the results. We perform a retrospective evaluation of automatically formulated queries compared to queries manually created for systematic review literature search. Note that we could not obtain a test collection of queries formulated using the objective method, as one does not exist. However, we leave this for future work. Here we compare the most effective queries in terms of F measure, precision, and recall. However, there's many more comparisons made in the paper, and you should see that for details. This table on the right illustrates the two best instantiations of our computational method. The first is where we don't add mesh terms to the query and optimize the validation set for F3, and the second is when we do add mesh terms to the query and we optimize the validation set for recall. We find that when we tune in the validation set, we overfit for that target evaluation measure. However, we can beat the original queries in terms of recall and precision, but we see a trade-off when doing so. We found that generally, adding mesh terms to a query increased recall with a trade-off in precision. Next, we ran a case study where we compare our fully automatic computational adaptation of the objective method to a query that was formulated using the objective method manually. To make this a fair comparison, only the development and the validation sets are used to compare, and no tuning was performed for the automatic method. We find that even using the other aspects of our computational adaptation, there's a reduction in the total number of studies retrieved, and this results in approximately $90,000 saving. Note the relatively tiny increase in precision in the table on the right results in approximately half the studies retrieved, while maintaining recall. We can also see the comparison between the actual queries formulated between these methods. On the left is our computationally derived query, and on the right is the manually derived query. We highlight the commonalities between these two queries to illustrate that our computational method does approximate the existing manual objective method. To conclude, we suggest that our fully automatic computational adaptation of the objective method is a good starting point for information specialists. Furthermore, we suspect that our queries can be easily refined by information specialists rather than having them construct a query from scratch. All human bias from the objective method formulation process is removed with our computational adaptation. We do this in two main ways. First, by tuning queries to allow them to be optimized for particular needs, and to evaluate the queries fairly on an unseen portion of studies, since we use the validation set for parameter tuning. In terms of future research, we split the test set into development, validation, and unseen using a random split. However, we don't know how sensitive queries are to this split, and so we'd like to investigate this sensitivity. The objective methodology only considers unigrams, and we model this in our computational adaptation also. However, we'd like to explore potential improvements to query formulation using n-grams. We would also like to undertake a prospective study using our fully automatic adaptation to determine what kind of real cost savings you get from using our computational adaptation of the objective formulation methodology. Thank you for your time and attention.